Okay, let's revisit the three different rules of do calculus, and let's try to understand them one by one. So the first rule says that probability of y given do t do z and then do t do z and the confounder w equals to probability distribution function of do t. Then we won't be having also sorry, it's first rule, right? So it is z, it is only z. We can, okay, let me, yeah, so it is z, and w is probability of y given do t, and we won't be having this z, we will be only having this w in a graph where y and z, they are conditionally independent given w in a graph where this thing will happen. So this is the first rule. Second rule is the probability distribution do t, this time it's do z, and this time is w is equivalent to do t. Then we can replace this do operator and we'll be having this w in a graph where y and z, they are conditionally independent of w in a graph of this and this. And rule 3, which is the trickiest one among all these three, so this is do t do z and w, this will be equals to y given do t and w. So we can completely remove this do z in a graph where y and z, they are conditionally independent of w in a particular graph where this is this, and there is something called as this. Okay, so we are having this do t operator in each of these three rules. So this conditional independence, this will hold also. We have to include the t after this conditioning bar. So this is actually the three rules of do calculus. Now let's analyze them one by one. So before we can proceed, what do I mean by this type of graph? So what is this t bar? So first of all, t is my treatment, then y is my outcome. And so when I say something like, so when I'll be having a graph like this, a b c, suppose here it is d, something like e, so this is a graph, right? So when I'll be saying something like this, so when a bar on the downside of a, this means that we have to remove all the edges that are going out of a. So in this particular graph, there is this edge that is going out of a, so GA will looks like something this. So this is A, this is B, this is C, this is D, and this is E. So for example, something like this will also happen. So we will have to remove this particular edge as well. So this is the graph. Okay, so this is A down bar. If I say something like this, G of say D, the upper bar, So it means that what are the edges that are in my original graph, what are the edges that are coming to that particular node. So here we can see that this edge is coming to D, so we have to remove this. So this graph will look like this A, then B. The other nodes, they will be intact. Okay, and this is this. Okay, so these are the two things. So one of the common things that is we can observe in all these three rules, that is this particular thing, GT upper bar. So why does this happen? Why is this happening? Because we are trying to do this, we're trying to measure Y while do T. Now in a typical graph like this, this will be the causal path, and there will be something like this, then something like this, something like this. Okay, so when we'll be doing this do T, it means that we have to consider the graph, the causal graph, where we have to remove all the incoming edges to this T variable. So we have to remove this. Okay, so let me do it again. So this is my original graph, and this is my causal graph. Okay, we actually removed these three edges. Okay, because we are doing this duty. So that is why, in all these three cases we have this T bar. So our main concentration will be to understand this, what is this T bar. Okay, now, okay, so let's analyze the first three rules one by one. So let me remove this I won't be requiring, and going forward a lot of things that I'll be saying, they are, you will be able to find it in the lecture notes of Brady Neal, but I'll be trying to present it in a different way. So let's do it. Now this part is actually taken from Brady's lecture. So in each of these three cases, how we will be understanding this particular thing is that we will be considering this T as null. Okay, so then my first case will be probability of Z and this guy is do T W if Y and Z, they are independent. Okay, they are conditionally independent given W. My second rule is Y with a do Z and W, this thing will be probability of Y. Now I can remove this guy and I'll be having this Z G W in a graph where I have to remove this guy. Okay, and the third rule, which is the trickiest of them all, we'll be having this do Z and we'll be having this W, and we can remove this Z completely from our distribution, and this is something like this G of Z W bar. Now what is this guy? Okay, we'll be seeing that one after the other. So now if you saw the lecture of Brady, again I'm reiterating the same fact. This guy, this rule is the generalization of backdoor criterion. I'm sorry, this is the generalization of D-separation. This is the generalization of backdoor criterion. and this is not a generalization of any particular rule, but this thing is actually there because we want to avoid the colliders. Okay, so let's understand the first rule. So let's see what d-separation is all about. Okay, so d-separation, which is also called the global Markov assumption. So if we are given a particular graph G, and if we can say that A and B, these two are the random variables, they are d-separated in the graph by some third variable, this will indicate that A and B, they are conditionally independent given my third variable. Okay, interesting. So this is why d-separation is very important. So yeah, so A and B, they are conditionally independent in the distribution. Okay, so how we can prove that two variables are d-separated? So that is a separate video, but I am going a bit faster here. So in this case, A and B, they are d-separated by a third variable C if first we have to consider all the undirected paths among A, B and C. I'm sorry. Yeah. Okay, so this is the first step. Okay, so it may happen that there exist multiple paths among A, B and C, so we have to consider all the paths. Next, all the paths should be blocked. Okay, and we have to consider every triplets in the path and check for fork, then chain, and 3 immoralities or colliders to say which path is active. So I can give you one example. I think that will be quite good. So for example, say this is A and this is B, this is C. Suppose we have E. Okay, so there is this path. Okay, let me do this. And there is this path. There is this path. Okay, there is another path. There is another path. There is another path. So it's a DAG, directed acyclic graph. So first thing, what you need to do, we need to check for this thing. A and B, they are conditionally independent with respect to C. So first we have to see that what are the paths that are there from A, C to B. So this is one particular path, right? And this is also another particular path. So we have got 3 paths. Okay, so let me do this. There is this D, there is this guy, so we are having this path. So we have to consider that these paths first of all, they are undirected. So I mean, yeah, it will be easier if this graph will be a bit more complicated. Then you have to consider like this. Okay, why this thing is written, that this undirected thing is going on, that you may have some sort of graph where you may have a path from, for example, you may have something like this. Okay, and you don't have it because it's a DAG. So you are having a path from A, or rather I'm sorry, you will be having something like this. Okay, so you don't have a path from A to B, okay, but you have a directed path from B, G and A. So you need to consider this path as well. Okay, whether any information will be flowing from A to B, so you need to consider this path as well. So that is why this undirected thing came. So let me remove this and let me go back to my original graph. Yeah, so now we have to check this path, and we have to check for every triplet. So if you see this particular path A, C, B, it's a chain, it's a chain, right? And we are actually conditioning on C. So in this particular path, for path 1, A and B, they are conditionally independent given C. So for first one. So now we have to check for the second one as well. Now if both these two paths, there we are able to find that no information is flowing from A to B, then we can say that this condition holds. So if we see that, so we have to consider this triplet. So A, D, G. So this is again a chain, and we are not conditioning on D. So information is actually flowing from here to here. Okay, and okay, so there is also another path. So there is 3 paths. So one is this guy, another one is this, and this. So we have got 3 paths to consider. Now information is coming from A to G because we are not conditioning on D. So now we'll see D, G and B, and here also we haven't we are not, so this is D, G and B, and also here we are not conditioning on G. So information will be flowing from D, G, B. So first again, for the second case, so we are considering this path A, D, G, B. So first we are taking this triplet A, D, G. This is a chain, and we haven't we are not conditioning based on D. So information is flowing from A to G. Next we are going from D, G, B, and here also the information is flowing, and this is also a causal chain, and we are not conditioning on G. So information is flowing from D, G, B. So this path A, D, G, B, this whole path is active. So we have got one particular path which is active, which makes this condition void. Okay, now how we can make how we can deseparate A and B? What are the extra nodes that we can include after this conditioning bar to make these two variables conditionally independent? So for example, in this case, if we have something like this D, so now this A, D, G, this path is a chain, and we are conditioning on D. So it means that this path is block. So this path is block. Okay, so no information will be flowing from A to B. Okay, so this path, I'm sorry, this path, this particular path is inactive. Okay, so this is inactive, this is inactive. We have to check this third guy. So let's see this guy, A, D, then G, then C, then B. Okay, so again, so if you see, we are conditioning based on D. So information will be flowing from here to here to here to here, but this is a causal chain. We have to consider every triplets. So we have to consider this particular triplet, and this is a chain. This is a chain, and we are conditioning on this guy, D, the middle guy, which makes this particular path inactive. And if you have got one inactive path, then the information won't be flowing from A to B. So this path is also inactive. So we have got three paths, and three of them are inactive, which makes this condition holds true. So we can say A and B, they are d-separated in the graph given C and D, which makes it A and B, they are independent in distribution given C and D. So this is what d-separation is. Okay, now if we check this first condition, so the first condition says that probability of Y given Z and W is nothing but probability of Y given W if Y and Z, they are independent given W. Now what does that mean? This is nothing but we are seeing, we are again seeing that we are actually in a graph where Y and Z, they are d-separated. They are d-separated by a third variable, W. And this means that if this thing holds true, that in a graph where Y and G, they are d-separated by W, so in the distribution, Y and Z, they are also conditionally independent given W. So that's why we are not including Z after this conditioning bar. So this again we can write like this, that in the graph that this holds true. So in the distribution, this thing holds true, and that is why we can say that probability of Y given Z and W, as Y and Z, these are independent given W, we can remove this. Okay, so that is why this first law of docalculus is a generalization of d-separation. Okay, it's easy, it's cool. Let's see the second condition, or the second rule of docalculus. So the second rule of docalculus says that if we have something like this, then we can remove the do operator. Okay, in a graph where if Y and Z, they are conditionally independent in this particular graph. So in the so first understand what is backdoor criterion is. So backdoor criterion says that if I have got something like this, so this is a confounder X, so there is this backdoor path from T to Y, and now this X, if I cancel this guy, this particular edge, if I remove this, and if I have got only this guy, so this is a fork, and this fork, if we condition on X, then T in this fork and y, they are conditionally independent on x. Okay, so this is what backdoor criterion is. Okay, I'm sorry, this is not a backdoor criterion, this is a general thing, but we are having, so what I'm saying is that this x is actually able to block the association that is flowing from t to y. So only the causal association remains. The the association from t to y is actually blocked by x. So if this is the case, then we can write something like this: t given, I'm sorry, y given 2t, this is probability, okay, is nothing but summation w, we can marginalize yw do t, and then we can have w, and we will be having something like this: t and w. Okay, so if I go by steps, this is this, and now in this case, as w, I'm sorry, it's not w, it's x, so let's make it w. Yeah, so as w is able to block the association between t and y, so we can remove this do operator, and this is simply this. So this is what backdoor criterion is. Okay, now one of the things, that what is the relationship between backdoor and d-separation. So it's very simple. So if you can see that w is able to block, so when I will be saying that a is d-separated from b given c, it means that c will block all association, or we can say, in causal inference literature, this is called as spurious association. So it will block all the spurious association between a and b, and also causal association. So in this particular case, we are actually seeing that this w is only able to block the spurious association between t and y. The causal association is still there. So if I go from this graph to this particular graph, where I'll be removing the edge that is going out of t, and we have something like this. This graph is d-separated. So here you can say that t and y, they are d-separated given w in a graph where I'm removing the edge that are going out of t. Okay, so this is interesting. So now we can also go from d, so this is where we are going from backdoor to d-separation. We can go from d-separation to backdoor. Okay, if we say that I have got this particular relationship, I am in a graph where the edge that are going out of t has been removed, and this conditional independence, this particular relationship holds, then I can say that w is a sufficient adjustment set. in the original observational graph G, which is like this, right? Okay, so we all know that generally this graph is called the observational graph and this graph is called the manipulated graph. So this is our observational graph, and our main aim is to find out the causal effect of y given this do t. So we are interested in this graph, we are not interested in this particular graph. But if we come from this manipulated graph to this particular graph, okay, and we are given that in this manipulated graph I've got this conditional independence relationship holds, then we can say that W is my sufficient adjustment set. So in the original graph we can also say that this W satisfies the backdoor criterion. Okay, because it is able to block the spurious association between t and y. So then we can write like this: probability of y given do t is nothing but equals to, this is w y given t and w. Okay, we can remove this do operation. Okay, so now we actually went from d separation to backdoor criterion. Now the second rule of do calculus is exactly the same thing. Okay, so we are given in a graph where we are removing all the edges that are going out of z, and in this particular graph we have this particular relationship y and z. They are conditionally independent given w in this graph. If this is the case, then we can say that probability of y given do z w is nothing but y given z and w. Okay, so basically it says that, okay, now so basically it says that in the graph where we have removed all the outgoing edges from z, then, and also in that graph, so okay, just forget it. So if we say that we are in a graph where we have removed all the outgoing edges that are going out of z, if we remove them, and also in this particular conditional independence relationship holds, which says that y and z, they are conditionally independent on given w, then in the original graph, so this thing is in the original graph, we can remove this do operator and we have this relationship. Okay, and this is exactly the same thing with this guy. Now you may say that, okay, there is no w here, how this guy is equal to this, there is no summation. So if y given do t is nothing but, if I do a marginalization with respect to w, okay, do t, next is w, I'm separating out, I'm using the product rule of probability, y given do t and w. So in this particular graph, my w, this is the original graph, my w is able to block all the spurious association between t and y. So now this guy is nothing but equals to t and w. So this relationship is nothing but this relationship. Okay, so that is why this second rule is the generalization of backdoor criterion. Okay, so let's do a brief recap what a backdoor criterion is. So this is the backdoor criterion. So my W is able to block the spurious association between T and Y. Only the causal association remains. So if this is the case, then we can say that this thing is equal to this thing. Okay, now backdoor criterion from D separation. So if we have this graph, and if we remove this particular edge which is actually going out of T, and we have this graph, and in this graph if W is able to block all the association between T and Y, then we can say that T and Y, they are D-separated given W. So first we are having this graph, from this graph we are coming to this graph, and in this graph we are seeing that this conditional independence relationship holds. So that is why it calls that we are coming from backdoor to D-separation. Now if the reverse thing happens, so first we are given a graph where this thing holds, and in this particular graph all the edges that are going out of T has been removed. Then we say that W is the sufficient adjustment set. So in the original graph we can adjust for W. Okay, so in the original graph we can adjust for W. So this relationship holds, and if we try to marginalize this, and if we use the product rule, we are having this thing. So in the denominator, sorry, in the, so we are still having this do T after the conditioning bar, and this do T can directly be removed because this W is the sufficient adjustment set. So we are in a graph where it is D-separated, and there we can apply the backdoor criterion to get this relationship. So this is nothing but, this thing is nothing but written in the rule 2 of docalculus. So that is why, so what docalculus says, that we are in a graph where this conditional independence holds, and also we have removed the outgoing edges from Z. Then what we can do, that we are given, so we are trying to estimate the Y given do Z and W, so we can remove this do and we will be having only this Z. So this is a causal estimate and this is a statistical estimate. So I am repeating the terminologies from Brady's lecture. So we are having this causal estimate, and this causal estimate can be estimated with a statistical estimate, and this is our observation actually. So this is our main idea, that we have to remove the dues. So I hope it is clear. Now let's go to the third rule. Now before going to the third rule, let me iterate once more from backdoor to D-separation. I hope that this particular thing will be new. Okay, so this thing satisfies the backdoor criterion. Why? Because this W is not a descendant of T, and this W is able to block all the spurious associations between T and Y. So that is why this W satisfies the backdoor criterion. Okay, so important. So this W blocks, spurious association between T and Y. Okay, this is very important. And so that's why if we go from this graph to this graph, where we'll be removing the outgoing edges from T, so this is W, this is Y, this is T, we can say that t and y, they are deseparated in this graph. Okay, so before jumping into this graph, we have to understand that this w has already blocked all the spurious associations. Only the causal association remains, which we have removed by going from this graph to this graph. So this is from backdoor to deseparation. Now, what is the third rule of docalculus? So the third rule says that we have got this probability distribution do z and w, because we assume that this t is null. If I think I have mentioned, yes, so the t is null, so we can remove probability of the z. We can remove this z entirely if y and z are conditionally independent on w in a graph where this is a peculiar condition. So generally this means the nodes in z that are not the ancestors of w. Okay, in G. Okay, so we are considering this particular graph. So now if you remember that our original rule says something like this: do t when t is not null, we have this gt bar and I'm sorry zw. Okay, so in this setting, when t is not null, we'll say that zw is the nodes in z that are not the ancestors of w in g t bar. So in this particular graph. Okay, yeah. So because we set the value of t as null, so we are in G. In this case, we are in this particular graph, so this condition will hold when we are in GT bar graph. Okay, so let's remove this. Now let's understand what is the utility of this particular node. Okay, yeah. So let's I think I have the yeah. So let's have something like this. So this graph is taken from Brady's lecture. Okay, so before that, I think before going to this, let's understand one thing, that we are actually in a graph where we removed all the edges that are coming to this node Z. Now forget about the ancestors and all, let's consider this Z. So first we need to understand that how this graph will look like. Okay, so if this is my ZW and these edges which are coming to ZW, we are removing this. Okay, now it says that Y and Z, these two are conditionally independent. Now if now this thing can possible if this is a causal chain, okay, or this thing can be possible if this is a fork, right? Now it says that Z are not the ancestors of W in G. Okay, so here also we are removing these edges. Okay, so I think I made a mistake. I'm sorry. So W can be in the middle of a causal chain, or W can be in the middle of a fork. Okay, now let's think about it, whether this thing can be possible or this thing can be possible. Now we are actually in a graph where G of Z upper bar. So this upper bar means that we have to remove all the edges that are coming to Z. So we have to remove this edge. And in this particular graph, we are seeing that the conditional independence relationship holds. Okay. So because we are in this graph and this thing is happening, so yeah. Now if we remove, now if we consider this kind of graph, and here also from this graph we have to remove the edge which are coming to ZW, so we have to remove this guy. And after removing this guy, we can see that the conditional independence relationship, this relationship doesn't hold for this particular graph. Okay, so let's do one more recap. So the third law says that we have to be in a graph where we have to remove the edges that are coming to Z, and in that graph, after removing the edges which are coming to Z, if this conditional independence relationship holds, where Y and Z, they are conditionally independent given W, if this holds, I'm sorry, let's do one more recap. So we have to be in a graph where we removed the edges that are coming to Z, and after removing the edges, so I think it's better that I write it. So let's yeah, so let's do step by step. So to get this, first we are in a graph GZW bar. It means, which implies that we removed the edges to ZW, and check in GZW bar if Y and Z are conditionally independent on W. Okay, so yeah, okay, now we are not considering whether the ZW is should not be an ancestor of W or not. No, we are not considering. So we are given this particular condition. So to get in this condition, first we have to come to this particular graph, and we can get this graph by removing all the edges which are coming to ZW, and we have to check whether in this particular graph this conditional independence relationship holds or not. Okay, so how these two things can be possible? If in my original graph G is something like this, W, Z and Y, if W is in the middle of a causal chain or W is in the middle of a fork, right? Now we have to go from this graph to this graph. This is step one. How we can go from here to here? And also remember okay, yeah, y z z y, yeah. And also not this, this is this, yeah. And also and also that in this particular graph we may have this kind of things, right? So there are some other nodes, you know, which actually have edges from that node to z. So we have this kind of structure. So this is A, this is B, okay? And we have to go from z to z, we have to go from g to gzw bar. So how we can get this graph? We have to remove the edges that are coming to z. So we have to remove all the edges, okay? So these things are gone. So we only have this thing. So we can clearly see that in this particular graph, if we condition on w, z and y, they are conditionally independent, okay? So this particular structure can be a member for satisfying rule 3 of docalculus, okay? This type of structure in my original graph. Now let's see here. So we have to go from this graph to this type of graph. So we have to remove this guy, okay? Now we can see that w and z became independent, okay? And we don't have this conditional independence relationship holds for this particular graph. So this type of structure, this type of fork structure cannot be a member in my original graph G, which can satisfy rule 3. Okay, so if you see the Brady's lecture, you can see that we'll be having this type of causal chain, and that is actually the reason why he has this type of causal chain, because you know, this fork we cannot have it because we have to remove the edges to z, and if we remove the edges from to z, then we will not be having this conditional independence relationship. So okay, now let's see why this zw shouldn't be an ancestor of w. Why, in other words, why this zw shouldn't come before my w. So let's have a graph like this, a b, and this graph I'm taking from Brady Neal's example, and I have this, and I have this, and I have this. Okay, so you can see that this is my original graph, and in this original graph I'm having a chain because I cannot have a fork. Okay, yeah, I cannot have a fork or something like this. A b, so we having some w, so a to zw, b to zw, and then this and this. Okay, so I cannot have this sort of relationship, and also this, because this when I'll go from G to this graph, I have to remove this guy. Okay, and in this particular graph, this conditional independence relationship won't hold. But if we remove these two, still we'll be having this relationship. Okay, that my zw and y, they are conditionally independent given my w. Okay, so that's why we won't be having this fork. We'll be having some sort of chain in our main graph, but actually, you know, you also can have this kind of chain because the z W cannot be an ancestor. Now let's see why. Okay, so let's see why. Now in d-separation, so if we go from backdoor to d-separation, so in a backdoor criterion, we can have this sort of graph, and we say that if W blocks all the spurious association between T and Y, we can go from G to GT bar, and we can remove the edge from T to Y. Okay, let's frame it in another word. So if we have a graph where my W is able to block all the association between T and Y, only the causal association between T and Y are there, and if we remove that causal association in a manipulated graph, then we can say that in the manipulated graph, W d-separates T from Y, and this W is called the that minimum adjustment set or sufficient adjustment set. Okay, so now here we are conditioning on ZW. Okay, so sorry, we are conditioning on W, so we are conditioning on this guy. Okay, now in this particular graph, so I'm actually still in my original graph, this W in my original graph doesn't block the spurious relationship between ZW and Y, or it doesn't block the spurious relationship between the other nodes. How? Because this ZW is a collider, and I'm conditioning on the descendant of a collider. So when I'm conditioning on the descendant of a collider, we are having, I don't know. So when I'm conditioning on the descendant of a collider, I am having this association active. Okay, and when I'll go from G to GZW bar, okay, this path, I'm sorry, so in the original graph, I'm conditioning on the descendant of a collider, so I'll be having this path active. So when I'll go from this to this path, oh gosh, so this is B, this is Y. Okay, so let's do a recap. I'm sorry because of this disturbances. So in my original graph, I'm conditioning on the descendant of a collider, and I'll be having this spurious path from A to ZW to B to Y, and when I'll remove the edges which are coming to ZW, still this spurious path will exist. Okay, so I cannot say that my Z in my manipulated graph, my ZW and my Y, they are conditionally independent. So this is actually the reason why ZW can't come before W, or in other words, ZW cannot be the ancestors of W. So this is the main utility of the third rule of docalculus. Let's go once more. So we are here, we are actually in the backdoor criterion to deseparation. So if my W blocks all the spurious association between T and Y, then in the manipulated graph we can say that W deseparates the T from Y. But the important thing is that in my original graph, W should block all the spurious association between T and Y. There shouldn't be any spurious association between T and Y in my original graph. So if that happens, then I cannot go from G to GT bar. But I'm sorry. So if we can take the same concept from here, we have to understand that this W in my original graph should block all the spurious association between Y and Z. Okay, if that happens, then in the original graph, if I remove the causal association, so in my original graph, if W is able to block all the spurious association between Y and Z, then we come to the manipulated graph, and if we remove the causal association between Y and Z, then we can say that Y and Z in my manipulated graph, they are deseparated given W. I know it's a bit heavy. Again, if in my original graph G, W, if in my original graph G, the node W is able to block all the spurious association between Y and Z, then from G to G of ZW bar, when you come from G to ZW bar, and in GZW bar, if we remove all the causal association between Y and Z, and if we say that they are conditionally independent, then this particular relationship holds. Okay, so I don't know whether you have understood it or not. Let me try it again. If in my original graph, if W is able to block all the spurious association and no spurious association should be there in my GZW bar, okay, so if this happens and this condition happens, then we can say this equals to this. Okay, but if you check in my original graph, I have some structure like this, and here the ZW is the collider, and we are conditioning on the descendant of a collider, so we have this spurious relationship, this path. So when I'm going from this to this active path is also there, right? So this active path is also there because W is not able to block all the spurious relationship between ZW and Y in my original graph. Okay, so I can't go from here to here, and we cannot say that in this particular graph this relationship holds. Okay, so let's do once more. We are given this particular graph and we are conditioning on the descendant of a collider, and we are having a spurious path. So W is not able to block all the spurious paths between ZW and Y. So we cannot say in the manipulated graph that we don't have any path from ZW to Y, because there is this spurious path that actually come from this graph. Okay, so because in the manipulated graph we are not able to have this conditional independence relationship, we cannot say that this guy should come before this guy. So in my original graph, to hold this condition in my manipulated graph, in my original graph, ZW shouldn't come before my W. So this is actually the three rules of due calculus. We'll solve a particular problem, and we will again analyze all these three rules. So let's end here.